Alright, so with similar triangles, I've done my best to draw a couple similar triangles here, but where they're not perfect, I've tried to label it to indicate what's happening. So essentially a similar triangle is just like Honey, I Shrunk the Kids sort of thing, where you just shrink one triangle down, or going the other way where you make it big, like Ant-Man. So anyways, they're the exact same thing in proportion to each other, but they're different sizes. So the important things to note here is, first of all, the related angles are congruent. So by related, we mean they're related to each other. So A here, we would say, is similar to D, and they're equal. And I've marked them with tick marks to indicate the equality. C and F are equal, and then B and E are equal. So not all the angles of the triangle have the same measurement, but they all have these ones that they each have an angle they relate to that are equal in measurement. So, you know, what you can infer from that is all equilateral triangles, because they all have the same angles, also are going to be similar to each other. But here we have scaling triangle, two scaling triangles that are similar to each other. So the lazy way that's said sometimes is that all the angles are the same, and that's not what's happening, but they each have an angle that they relate to that are equal in measurement. Alright, so the second thing that's happening is that the sides are related proportionally. So what that means here, and I try to make this one really obvious so you can see what's happening, but the proportion, the ratio here is a half. So, you know, 6 and 3 are related because 3 is half of 6. Now, if we have that relationship there, it has to be the same relationship for all the sides. So 8 and 4 relate by half, and 2 and 4 relate by half. If we had a pair of sides that related by half and another pair of sides that related by thirds, then that doesn't count. They have to be all related to each other by the same ratio. So a way to express this is to set up a ratio between the different sides. So side AB, let me just write it out over here to the side. So let's do DE first. That would be 3 inches over 6 inches. So those are my yellow ones. And that fraction reduces to a half, and that's where I'm getting that the ratio of the similarity is a half. But that equals 4 inches over 8 inches. That's my blue highlighted relationship. And that equals 2 inches over 4 inches. What makes these similar triangles is that I can put equal signs between these ratios of the different sides. Now with this, I set these triangles up to show you an example of two similar triangles. Normally when you're doing like an example problem, when you're working on an exercise, you don't have all this information. You have some of it, and then you use some of the information to determine other information. We'll do an example like that now. Well, before I go on to do that, I did want to emphasize one thing about setting up these ratios that I forgot to emphasize. If you look across the entire top of my fractions here, these are all from the smaller triangle. And if you look across the entire bottom here, these are all from the larger triangle, or the big triangle. So when you're setting up these ratios, you have to be consistent. The small needs to be on top, the big needs to be on bottom. Or you can put all big on top and all small on bottom, but you can't crisscross them. So that's going to be important when you're setting up the ratios yourself, that otherwise we wouldn't have a half all the way across here. We'd have a half equals to 2, and that's not true. Alright, so here's the diagram I tried to draw. And our directions are to find the length of side X. So first of all, before you can use any fact that they're similar triangles, this doesn't tell us they're similar, so we have to conclude they're similar, and then that allows us to use proportions to solve it, to determine the side of X. so the length of x. Alright, so if all the angles have a pair that they are equivalent to in measurement, then we know that they're similar triangles. They flat out tell us these two are equivalent. And so then the question is can I get another pair that's equivalent? If I can get a second pair that measure the same, then I know the third pair does, because two angles will force the third angle in a triangle since they all have to add up to 180. So one of the things we learned initially was that opposite angles, when we cross two line segments, the opposite angles are going to be equivalent in measure. And so once we have that, we know these third angles will be forced to be equal as well, because once you know the measures of two angles, that forces the measurement of the third angle. So we know they're similar triangles, but we couldn't do what we're about to do unless they were similar triangles. Alright, so now that we know that they're similar triangles, what we're going to do is set up a proportion or two fractions that are equal to each other in order to determine the measurement of x. This one's a little tricky because they're flip-flopped like this, and so it's sometimes hard, depending on how good you are at moving things around in your brain, but it's hard to see what parts are related to each other because of their orientation. For some people, it helps them if they redraw one of the triangles so that it's rotated the same as the other triangle. So what I'm doing here is I'm redrawing this triangle so it's rotated the same as the other triangle. So I'm not just flipping it over. I'm going to rotate this angle over to here so that it's in the same position as this angle, which is different than just flipping it over this way. Okay, so when I rotate that, then side X would be here. This would be my 8-inch side. Hopefully you see what's happening there. I'm rotating it clockwise 180 degrees. Okay, now once I do that, then you can see that the 7-inch side is related to the X side. I messed up. We need a 5-inch here. I just didn't get it written down for my notes. Okay, so then because we didn't have enough information otherwise. And the 5-inch side is related to the 8-inch side. And that's how we're going to set up our fractions. So what we have is, and again, we can put small on top and big on bottom or vice versa. So in other words, you could do 7 inches over X equal to 5 inches over 8 inches. So you could set it up that way. Or you can flip-flop everything. You can do X over 7 inches equals to 8, but messed it up, inches over 5 inches. Okay, either way you set it up is okay. In this first one we have the small triangle on top and the big triangle on bottom. The second one I have the big on top and the small on bottom. Now here's the deal. When solving a proportion like this, it's going to be easier on your life if the variable you're solving for is in the top or in the numerator. And so I like this setup just because of where X lands. It's not about small and big, it's about where X lands. And so if X lands in the bottom when you set up your ratios, just flip-flop everything. It just makes the algebra a little bit easier. You don't have to do that, but it does make the algebra easier. Alright, I cleared all that out and pulled my proportion over to the left to give me some room to work. Now here's the idea, is when you're solving for a variable, you need to undo what's happening to X. And currently what's happening to X is that it's being divided by. Fraction part means division, so it's being divided by 7 inches. So in order to do the opposite of that, I need to multiply by 7 inches, and whatever I do to one side, I need to do to the other side. Alright, so when I write it out, it looks like that. I emphasize that my 7 inches I'm multiplying in the numerator by making it over 1, because 7 inches divided by 1 is just 7 inches. But the gist here is that on the left, it's going to cancel and leave me with just an x, which is what I was wanting to do. I was trying to isolate x. Equal to. Now on the right, you can do this a lot of different ways. You can take 7 inches divided by 5 inches, and then multiply in 8 inches. What I'm going to do, because the 7 and 5 don't reduce, is I will actually multiply 7 and 8 and then divide that by 5. It'll end up being a decimal. And I know it's going to end up being a decimal because nothing there divides evenly. 7 doesn't contain a 5, 8 doesn't contain a 5, but what matters here is the math with the inches as well. This is where I say if you do the math with the units, they'll tell on themselves. So the inches are going to cancel out. So when an inch on top cancels with an inch on bottom, I'm left with just an inch measurement on top. So altogether, then that's going to equal 11.2 inches. And again, I know it's inches because I only have one of them left, so it can't be inches squared. So the length of my side X is 11.2 inches. Alright, so that's the idea with similar triangles and using them to find side lengths. You can also use the idea of similarity to find angles. It's just less complicated. It's similar to just using 180 degrees to find all 3 angles in a triangle. So now we're going to completely change gears again and talk about right triangles and the Pythagorean theorem.